Hi, I'm Dr. Scott Coffin with the California State Water Resources Control Board. In this presentation, I will provide an overview of California's research and investigations into PFAS contamination in our water resources. First, a little bit of background about my organization. I work for the California State Water Resources Control Board, or State Water Board, which is under the greater umbrella of the California Environmental Protection Agency. While our organization often coordinates with other boards, departments, and organizations within the California Environmental Protection Agency, PFAS has forced us to work together more closely and collaboratively than we've ever had to, simply due to the pervasiveness of this contaminant suite in many products and environments. As a result, our agency has become more adaptive and integrated, and can more effectively achieve our mission of identifying and controlling sources of pollution, assessing human health and ecological risks, cleaning up pollution, and promoting safer alternatives to problematic chemicals like PFAS. We are addressing PFAS through various research and regulations, including identifying impacts to the environment, establishing threshold and advisory levels in drinking water and in aquatic ecosystems, monitoring to determine trends, limiting uses in commerce and industry, and removing PFAS from the environment. It's important to recognize that PFAS is a massive class of chemicals, with somewhere between 4,700 and 10,000 unique chemicals, depending on how they're defined. We currently have analytical methods that can test for about 40 of these using standardized targeted techniques. We can qualitatively identify the presence of additional compounds using non-targeted and semi-targeted analyses, such as high-resolution mass spectrometry, but we're unable to quantify their concentrations due to a lack of standards for all of these chemicals. The PFAS chemicals that we can test for today is based on a combination of the chemicals that have been phased out because of their high toxicity in humans and the environment, specifically perfluorooctanoic acid, or PFOA, and perfluorooctane sulfonic acid, or PFAS, along with some of the chemicals that the industry has recently replaced them with. The upcoming slides will provide additional information on the PFAS chemicals being reported in those samples in the black box, about 40 or so. But I'll also show you the potential of what the total PFAS class might look like in the green box in a couple of water system supply samples. We're working with the US EPA to get a handle on identifying the PFAS chemicals that are in greatest abundance in our water resources. Starting in 2018, we initiated strategic efforts to identify sources of PFAS in the state. At the time, we didn't have a roadmap on the types of industries in California where PFAS were being used. So we used investigative results from other states as a starting point to identify those industries where the highest impact could be found in our drinking water supplies. Fortunately, there are no PFAS chemical formulators in California, an industry with the highest risk to severely impact drinking water. However, some of our industries are using products containing PFAS as part of their industrial activities, and there are numerous consumer products containing PFAS being disposed of in our landfills. The water boards are focused on determining the extent of the impact of these sources. The industries under investigation are chrome plating facilities, airports, refineries, and bulk fuel terminals, wastewater treatment plants, and landfills. PFAS products are used as mist suppressants in chrome plating processes. Airports, refineries, and bulk terminals use aqueous film-forming foam, also known as AFFF, that contains PFAS. At these types of facilities, there's a risk of disposal of PFAS into waste streams, leading to subsurface contamination into secondary receivers, such as a wastewater treatment plant or landfill. Additionally, landfills receive consumer and household product waste that contains PFAS. They are also, in some cases, the recipients of sludge or biosolids from wastewater treatment plants. Likewise, landfill leachate is sometimes sent to wastewater treatment plants. The primary objectives of our initial investigations are to gather information on the occurrence of PFAS in California's drinking water sources and watersheds. The data is being evaluated to identify impacted drinking water wells and identify areas where additional work is needed to ensure that communities reliant on those drinking water wells are provided safe drinking water, or where additional public water supply well sampling would be appropriate. The data is also being used to inform additional areas where watershed-specific source identification efforts are needed to inform future investigations. We've sent orders to airports, landfills, chrome platers, wastewater treatment plants, bulk fuel terminals, and refineries. Most of these orders were one-time sampling efforts to determine the presence or the absence of PFAS. The wastewater treatment plants sampled quarterly over a period of approximately 1 year. Further investigations based on the results from these initial investigations are being conducted on a regional level. Overall, we found the highest concentrations of PFAS in soil, groundwater, and stormwater near airports, with median concentrations of over 5 parts per billion. We found moderate concentrations in groundwater, stormwater, and wastewater around chrome plating facilities, and moderate concentrations in groundwater at landfills and publicly owned treatment works. High concentrations are consistently found in these landfills, many of which contain high quantities of PFAS-laden industrial and commercial products. This graph presents the median concentrations of PFAS in samples collected from the source investigations and at the wastewater treatment plants. Note that the y-axis is in log scale. For any single analyte, the median concentrations are all below 100 nanograms per liter, except for in landfill leachate. Landfill leachate is a concentrated liquid waste stream originating from rainwater, surface water, or groundwater passing through the waste, which is contained at landfills. Overall, these are areas where PFAS concentrations are much higher at point source locations, but the occurrence data as a whole is indicating that statewide, based on the analytes measured, there are no widespread impacts. Understanding the role of government in perpetuating institutional and structural racism is essential to our work at the California Environmental Protection Agency. Redlining is a practice through which federal and local governments and financing entities have systematically denied public and private financial services to Black and other people of color. This set of practices included both race and environmental factors as criteria in assessing the perceived creditworthiness of neighborhoods, and led to many of the environmental disparities we see affecting communities of color across the state today. Comparing cumulative environmental burdens from pollution with historic racing housing practices reveals strong correlations. We found similar disproportionate impacts with PFAS and groundwater. The occurrence data of PFAS and groundwater is presented on this map in colored points, and the colored polygons represent cumulative pollution burden percentiles, with darker shades of blue representing higher cumulative impacts. PFAS groundwater concentrations are consistently highest in the communities that already have the highest pollution burdens from other sources, due to their proximity of industry to these communities. This is a simplified overview of two investigation approaches that a regulatory agency may take to investigate contamination. The traditional or conventional approach involves investigating sites using targeted analysis followed with targeted response actions. In the case of PFAS, when new compounds are discovered, we repeat the investigation and implement new response actions, much like a never-ending game of whack-a-mole. This approach of regulating chemicals one at a time is slow and reactive and may lead to ineffective management decisions. For instance, water systems might invest in granular activated carbon to remove long-chain PFAS like PFAS and PFOA. However, this technique is ineffective at removing short-chain replacement chemicals, for which something like ion exchange resin may be more preferred. We're exploring a class-based approach for PFAS that leverages broader analytical tools to discover contaminants missed by targeted methods earlier. We analyzed samples from 9 public water system drinking water source wells that had elevated concentrations of PFAS using 3 targeted analytical methods: EPA method 537.1, EPA 533, and the Department of Defense QSN, which includes 38 expanded analytes. We evaluated these samples alongside a semi-targeted method, which uses the total oxidizable precursors or TOP assay, and a non-targeted method that assesses total organofluorine using combustion ion chromatography. Overall, the targeted methods captured between about 1 and 32% of the total PFAS by mass. The targeted methods were in close agreement with the semi-targeted TOP assay. However, the EPA method 537.1 consistently underestimated concentrations. This graph shows the frequency of detection for analytes, representing groundwater at airports and landfills, influent and effluent wastewater, and groundwater at wastewater treatment plants. Each of these different locations are different colored lines. The red dots represent the analytes measured in drinking water using the current testing method required by the public water systems, which is EPA method 537.1, which includes 18 analytes. By using a coordinated approach of analyzing both the PFAS source areas and the public water systems in the same area, we were able to compare these results as shown in this graph to see some differences. There are at least 5 analytes that are being reported at elevated frequencies at the source locations that are not included in EPA method 537.1. Fortunately, these analytes are included in a newer testing method for drinking water, EPA method 533. This method includes 25 analytes and are shown in the graph as squares. The analytes reported by EPA method 533 also overlap with most of the list on EPA method 537.1. As such, our organization will be switching to this newer EPA method 533 so that public water systems will analyze those compounds reported at high frequencies, but also retain a selection of the analytes representing both the legacy, older PFAS chemistries and the newer chemicals. An important observation shown in this occurrence data is that the same analytes are being represented in all types of water samples. They include a mix of the older PFAS chemicals as well as the newer ones. Seeing these same mixtures may provide insights into the ability to use similar instrument technologies elsewhere. In drinking water supply wells, at least one PFAS analyte was detected in 65% of water systems that used EPA method 537.1. These systems serve approximately 16 million people in the state. However, no monitoring data is available for approximately half of the remaining population in the state. Apart from areas suspected to have contamination due to nearby industries, we don't know where we may find PFAS. Considering the high cost of monitoring, it's important to take a targeted approach to use our resources wisely. We already have massive data sets of water quality data, hydrological, soil, and geospatial data. We leverage this data and machine learning tools to predict where we might find PFAS in untested wells. We trained a random forest machine learning model on areas with known PFAS concentrations and used 14 hydrological and 16 geospatial features as predictive features. We also used co-occurring contaminants to predict PFAS occurrence. Some organic chemicals were found to occur frequently with some PFAS, such as tertiary butyl alcohol and specific conductants. Our random forest machine learning model accurately predicted PFAS across all matrices and was significantly more accurate than a linear model. The model predicts concentrations of PFAS in groundwater wells with a Spearman correlation of 0.64 and can discern wells containing concerningly high PFAS concentrations with an accuracy rate of 91%. Using a data-driven approach to select locations for monitoring would more rapidly identify contaminated sites and save resources overall. For example, if we monitored in 600 out of 1,400 source water wells in the state, we would only detect 40% of the total contaminated wells if we were just selecting these wells randomly. If we used our machine learning model, we would detect 85% of all contaminated wells. Our plans going forward include additional assessment, monitoring, and treatment. We will expand monitoring into surface waters along major rivers, leverage existing regional monitoring programs, and determine unknown PFAS using non-targeted analyses. This further non-targeted work is being coordinated with the EPA's Office of Research and Development. PFAS monitoring requirements are also being incorporated by some regional water boards at landfills. And as the EPA issues their PFAS monitoring requirements for NPDES permits, the regional water boards will begin that process to incorporate those requirements. Subsequently, the issuance of the EPA's Effluent Limitations Guideline will include source reduction requirements that will be incorporated into our pre-treatment program. Also, we'll be issuing orders to public water systems to use the new EPA Method 533. If you'd like to learn more about what California is doing on PFAS, here's a couple of links that may be of interest. Thank you all for your attention. If you'd like to get in touch with me, you can send me an email or find me on Twitter. You can also find the slides posted on ResearchGate.